Good afternoon. Yeah, I wouldn't carry this lot overseas. Okay, it's going to shorten your tea break, blokes. Anybody ever see the film The Graduate? I feel a bit like Ben when he was pushed in the swimming pool by his father. Except I did this all myself. Thank you, gents, and we haven't even done the talk yet. Yep. Okay, thank you. Okay, before I actually tell you what I'm really going to talk about, I'm going to take you through just a little bit of personal history, which might show you why I'm here doing this today. Here is the raising winch on my own tower. 20 years ago, when I put this tower up for the first time, I started to winch away. It was a second-hand tower. I used the cables that had come with it. I checked the cables along the length for any signs of failure. And the inner sections of the tower started to lift. Then all of a sudden, there was a bang, like a rifle shot, right by me. And the first thing I noticed was that cable running up there from the winch was not there. Okay, where has it gone? That neat little gap down there behind the back of the drum and the back plate was absolutely stuffed with 8mm steel cable wrapped up on itself. It had gone at the top of the tower, which is 4.5 metres above that point, 5 metres above that point, and it had all stuffed itself down there. Now, where do you think I was when this happened? Well, I was there. One arm of me was on that winch. Had there been the slightest deflection on that cable, I might have been doing this to you with one arm if I was lucky, or not doing this at all if I wasn't. So, if you've ever had a cable go on a tower and you're still here, congratulations. If you haven't had a cable go, you don't ever want to be there. Even 20 years on, it still makes me cold thinking about what could have happened at that point. Now let's turn the attention to where I want to be today. This is the other winch on my tower, the one for tilting it over. Now look where that cable runs. It comes up from the tilting section. You're there already, yes, yes. Comes up there. Where are you when you're winching? If that cable goes, if you're lucky, you'll need a longer leg in your trousers. Plus probably an extension on your back, because where's the tower going to come down to when the cable goes? Yeah, it's a very, very dangerous situation. We can see the humour in it, but I wouldn't want anything to happen to anybody from this situation. Now, okay, I'm using commercial towers, most of us do for our terrestrial stuff. If you're playing on 2 metres, 70 centimetres, 6 metres, you may also use a commercial tower to support your arrays. If you're higher band stuff, you're probably using some other structure. But the principles apply, whatever you're doing. Doesn't matter. If you're anything that you're raising or winching on a cable, the principles apply, and most of what I'm going to talk about and are provided in the proceedings and the DVD can be used in that respect. So fundamentally, I'm going to be talking about telescoping towers, looking at the issues. We've shown the human safety aspect of that. I don't need to explain why it's important. I think we've shown that. So what I want to look about is, what can you do? How can you understand this? And I realise this is an after-dinner slot, and you've all enjoyed your lunch. It's probably about time for the afternoon nap, isn't it? It would be for me anyway. So the maths is not going to be too hard. I'm not going to go through it in detail. I will show you at one point the most complex piece of maths in the whole thing. And you've already seen worse than this today. So it's really largely schoolboy physics. But it's just something we tend to forget. Now, before we really start, there are two types of tower fundamentally. Not only do the North Americans have a different language to us over here, they use a different method of raising their towers. Most of them in Europe tend to be pivoted some distance up the tower, and you have a cable going to that end, and the working bit is up here. A lot of the telescopic towers in the States tend to be pivoted right at the base and raised up. Now, the market's different. There are a lot more rigid, non-telescoping towers used over there. It's a different type of market. But those telescoping towers and tilting towers that are used tend to be more like this. I have covered those in the proceedings and on the spreadsheet on the DVD, but I'm not going to talk about them this afternoon because we're short on time. The difference is you can actually counterbalance, if you're so inclined, a European-style tower because that pivot is away from the end. You cannot do that with the North American style. There's a fundamental difference in the measures you might be able to take to reduce stresses. So back to my system again. This is what I had up in the early 90s, 4 18 elements for 2 metres, plus an AR40 up there, rotator, and a 16-element tonner on the top. So two 2-metre systems on the same tower, this for moon bounce and the two together for contests. Put this on central Germany and move that one around the UK. Made it nice and easy. After that, it took a mixture of towers, of antennas, for sort of all the bands through from HF to 70 centimetres, with masthead preamps and things like that. Nothing terribly heavy up there in terms of extra hardware, but quite a lot of metalwork. And that's a 20-foot steel pole in the centre there. And the most recent it had until a couple of years ago was a 1.5 metre dish with a masthead, transverter and PA system, plus 2 metres and 70 centimetres above it. Now, in sighting this dish just above the top bearing, what I took into account was really the windage. Because obviously I didn't want it too high up to place too much stress on there. That was the reason I lost the 2-metre array for the EMI stuff. That was on an aluminium scaffold pole, and eventually that fractured 2 or 3 inches above the bearing. I didn't want the same to happen here. I didn't actually consider at the time the stresses in actually raising the tower. But when you start to put PAs and heat sinks and things like that up there, that's a considerable amount of weight. And it's that sort of crazy action that I want to talk about, because microwavers tend to do that sort of silly thing. We like to get lots of bands on top of our towers. Every band requires its own system. It's not like HF where you can put one thing up and that solves it all. You need something separate for every one. So I had chosen a worm drive winch. My tower actually came without winches. They weren't manufacturer supplied. It was an old tower, so I had to find some new ones. I decided right from the start that I did not want any risk of any slippage or clutches or brakes on the elevating winch. I went for a worm drive, and I can let go of that at any position of the tower raising and it stays there. However, I was being nosy. MoonNet, people announce systems they're closing down and that sort of thing. Gerard, PE1BTX, put out a note on MoonNet that he was selling up his 2-metre and 6-metre EMI system. I thought, well, I'll go and have a look, see what he's got. It's a sort of socially acceptable remnant of that characteristic you have as a 14-year-old. You know, how much has the other bloke got? So I went and had a look, and I found that on his 6-metre system, he'd put this huge cage on the bottom. Now, I'd thought about counterbalancing my tower. A few odd blocks of concrete bolted on, 50, 60, 70 kilograms. I thought, what on earth is he going to put in there? reading the page, that cage is designed to take 900 kilograms. For the metrically challenged, that's about 1,900 pounds of weight. And I'm thinking, why does he need that much? Okay, he's got four 6-metre, big 6-metre Yagis on the top, but he's obviously done some sums. It's time I got my calculator out. So, first thing you need to know is dimensions of your tower, or the structure you're working on. If you're lucky, you've got the manufacturer's data. If you're even lucky, you know where it is. I'm sure a lot of people have had the manufacturer's data, but you ask them to find it. Yeah, so otherwise, for me, it was a job out there with the tape measure and calculator. So, literally, going back to first principles, what is the total volume of steel in the tower for each section, and work out the mass, knowing the cubic mass of steel. It sounds a lot more than it actually is, and actually, if you want to do it, it's all coded up on the spreadsheet that's on the DVD anyway. So you don't have to go through the maths, you just do the measurements and put it in for your system. And that, I promised you the most complicated formula involved. There you go. That's it. There's nothing more complicated than that in this. You can all do it if you wish to. So once you've got the data, the two key things you need to know are, what is the mass of tower, that's all sections together when it's collapsed, below and above the pivot. Those are the key areas. And we can then start to model it using beam theory. Not electron beam theory, but the good old schoolboy mechanical beam theory. And I'll take you briefly through part of that, but again, it's coded on the sheet. You don't really need to do too much about it. We need to go back and remember a few things. Force is mass times gravity, or mass times acceleration, but in this case, the only acceleration we're worried about, unless something goes wrong with the winch or the cable. Well, even then, it's still gravity, isn't it? Gravity's the one that does the damage. So we need to work out the moment of on each side of the pivot, using moment equals force times distance. And taking measurements from my own tower, total mass of all three sections that I use at the moment is 245 kilograms. My pivot point is 1.82 metres above the bottom of the tower. So if I come to halfway along there and put the 71 kilograms that sits in that section as a force acting there, and the residual 174 kilograms of that section halfway along that bit, I can then do the force times distance calculations. In a lot of schoolboy stuff, they teach you that the beam itself is of negligible weight. So we all understand the principles of moments from that point of view. It just gets slightly different when you actually have a known weight in there, and you have to apply that. And you apply it as a single force halfway along the uniform section. And it's called the uniform distributed load principle. But that's just the tower. Oh, let's just go back a moment. As you can see, the clockwise moment, the force trying to turn it this way, is 3,773 newton meters, and the anti-clockwise is 638. So there's an excess has to be applied there to make this start to lift. And anybody who's done this knows it gets a bit heavy on the winch as you go. So now let's put some hardware on the top. A rotator and cage. Typical cage is going to be about 30, 35 kilograms. And for my tower, that would place it, the centre of it, at about 4.9 metres away from the pivot. Stub mast. It's assuming you go the whole hog, full 20-foot steel scaffold tube. They weigh about 35 kilograms, about 70 pounds. And that would place the centre of that mass at about 7.9 metres, getting on for 8 metres above the pivot. We're starting to get a long way away now. Antennas, well, how much does aluminium weigh? Depends what you've got up there, doesn't it? It's totally dependent on your own system. So let's say 10 kilograms. You can either model individual antennas if you know the weights, or you can amalgamate the lot and say roughly there is the centre of the array. There's a lot of assumptions in this. But you're going to be closer than not doing it. So let's say that, and let's say you've got something quite meaty up there. I mean, for the moment I've got a 10 gigahertz transverter and PA waiting to go up on the mast, and that's a good 20 kilograms. So even if I place that fairly low down, it's going to be around 6 meters away from the pivot point. So you'd obviously need to go through that for whatever system you're trying to work out and put your own numbers in there. But there's a diagram of what we've just had on that slide fully loaded up. The original tower, same values. Rotator and cage approximately 1 meter long, which places that about 50 centimeters beyond the end of the tower. I've aggregated the cage and rotator into one mass applied at the center. Most of the mass in there is actually the cage, so it's reasonably uniform. The rotators, a typical rotator, unless you're using something really heavy, is about 4, 5, 6 kilograms. The stub mast is applied as a single force at the center of the length of the stub mast. So there's the 35 kilograms from that. And these are two single forces, that for the antenna array, assuming that's the center of whatever array you've got, and that as a single force mounted where the hardware is. Now, our clockwise moment has gone up from 3,000 odd to 10,500. This has made a huge difference. No change on that side, but of course the force we now have to apply this side to start to raise that is an awful lot more. There's the sums. Multiply and divide, nothing complicated. 10,586, so the excess force we have to apply on this side is 9948 Newton meters. And just a word, for those who want to look at the North American stuff on the DVD, it's also coded in foot-pounds. So you've got both sets of values. I did the conversions for you. So the moment we have to overcome to start the thing moving is 9948 Newton meters. We have a 1.82 meter isosceles triangle at the point where we start to raise the tower, which makes it nice and easy to work out the starting issues, because that's the tower laying horizontal, that's the ground post vertical, and that's the cable that's going to take the stress. So, first of all, the force required is 9948 divided by 1.2. When you do this calculation, you don't apply uniform distributed loads. You don't want to know what the force is there. It's irrelevant. You want to know what it is here, where your cable is. So coming back this way, you work with real lengths. So that's the force in newtons, but we need a mass, a tension, not a force. So we have to divide that by gravity, which gives us 557 kilograms, or just over 1,200 pounds of tension required. That doesn't sound too bad, but that's the vertical force. We're going to be applying it 45 degrees. So we need a further stage. We need to divide by the cosine or the sine of 45. You can take it, for once you can take your choice. You cannot pick the wrong one in this. Well, you could pick tangent, I suppose, but as long as you don't pick tangent, you've got the right answer here. And you actually come out with 788 kilograms, or 1,700 pounds, is what your winch and cable has to supply. That can be quite a revelation if you haven't looked at that before. The recommendation from my tower manufacturer was that the luffing winch was a 1,500 pound pull winch. With a good head load, that's over the limit for that. So it's easy to exceed head loads. And I think we normally think about head loads as what the tower will take when it's actually standing vertical, once you've got it up there. But there's also issues in getting it up there. So what can you do about this? Well, you can provide some extra mass on the lower section, which is what Gerard had done, which is what brought me into this. A cubic metre of concrete will give you 2,400 kilograms. A cubic metre of steel will give you 7,850. A cubic metre of water will give you 1,000 kilograms. there are advantages and disadvantages to each of those. Water is great, provided you can get the container on there, because you can fill it when you need it and empty it out easily. Concrete, the way that Gerard had done it, is for concrete paving slabs. Each, certainly in the UK, a typical 2-inch standard slab weighs about 35 kilograms, about 70 pounds. So you're going to need quite a few of those, as he had in his picture, in order to make a sensible mass. From the spreadsheet, you'll find out that, certainly for my structure, I needed something of the order of 400 to 600 kilograms of mass in that cage, or in that bottom section, in order to make a significant difference on that stress, to bring it down to a reasonable value. We do not want to balance the tower, by the way. We need to retain, I would say, 150 to 200 kilograms of downforce on the head, because the last thing you need is you take something off the tower and it's halfway up again. You do not balance the tower, please. But even if you do take a step like that, it's not a total solution. If you've ever raised or lowered a tower, you will know that once you take the bolt out of the bottom to release it and start unwinding the winch, the tower doesn't do much. Cable comes off the winch all right, nothing moves. So what do? You unwind a suitable length, you get round there with the scaffold pole and lever the bottom. By that time, the cable on the winch has all gone slack. As the tower takes its weight, it all gets caught up and it will then start to jump as you wind it down or wind it up again. This was Gerard's solution. Very neat. Ever followed a truck and seen those great big rubber suspension air? Right, 2 of those. One mounted each side, so we've got the same force each side. You can pump those up with a car foot pump. They don't need a lot of pressure. So you start to slacken the tower off, and you just gently pump these up, and it pushes it away until the tower will take its own weight and will come over. Very, very neat solution. Even if you don't do anything about counterbalancing, that is a neat solution to that problem of getting the tower going, and also when you bring it back down again. Because you've also got to take measures to stop it slamming home, haven't you? Which makes the whole array go like that. Bits may drop off, which you don't want because you're underneath them. I mean, you don't want it at any time, but you particularly don't want it then because you're underneath them. Hence the helmet. So that can be used in both situations. It's a very, very neat solution. There are some very large truck balloons, but there are also some fairly shallow ones. You just need to go and talk to your local breaker, because they generally put these in the bin. They don't reuse them. So you may get them for nothing, or at least very cheap. You don't have to go out and buy new ones. We're not in quite such a safety critical environment here. If it does rupture, if one does rupture, it's not going to really be the end of the world. Might be inconvenient, but that's it. The other thing that is applied by most manufacturers, fortunately, and this was the saving grace over my finding I had a £1,700 pull on a £1,500 winch, is that you get some mechanical advantage applied. On my tower, the cable runs from the base of the fixed section through the moving section and round. So that actually reduces the stress on the winch cable by a factor of 2. There are two lengths of cable running around there. Some of the Versa towers actually had 3 lengths round, so you divide it by 3. So my 1700 starts to look like 850, which is well within the capability of the winch, thankfully. There's another view, perhaps a better view. You just need to be careful which pulleys you take into account. If it's one that's simply changing the direction of the cable to get to the winch, it is not providing you any mechanical advantage. If it's one that is like this, multiplying the number of cable lengths you've got doing the pulling, then it should be taken into account in the mechanical advantage. Now, all of the information shown here is on the conference DVD. There are different pages to work out different things. One just to work out the basic tower information if you have to go and do the measurements, and another page where you can work out the moments and the balancing, and a further page to deal with the North American structures. So it's all there to have a play with. You may want to go in and reformat some of the formulas, but it's all basically in there. You can calculate the mass, the moments, the stress. We've got the structures, but most of all, you're going to have to modify it to suit whatever you're measuring. The fundamental assumption I've made in there is that you are dealing with some sort of commercial tower. But of course, you may not be. So you may have to just take some notes out of that and build something to suit what you've got. The outtakes. Every good DVD has the outtakes. It's a bit of a salutary tale. This is, I don't know how well you can see it from out there. Okay, not terribly well. This hasn't come out too well. This is the winch that's actually on my tower. And at the back of, this is the raising winch, not the tilting winch. At the back of there is the ratchet that is lined up with that sprocket. And that's as it should be. This is the winch that used to be on there, and after about 6 months of use, it's a pity you can't see that, because that ratchet is no longer lined up with that sprocket. The frame that holds it has twisted on a 2,500-pound pull winch. So that winch is useless, and that's one reason why I don't particularly like ratchet-type winches. Because if something goes wrong with that, there's no ratchet acting, or there would have been no ratchet acting. When that happened, the tower was up, and I had to bring that down, knowing that I had to keep control of that at all times. I could not let that go. So hopefully I've shown you the potential danger. Counterbalancing may be an option that you want to try. Doesn't matter. Most important thing is that you're aware of the danger, and it's then your decision as to whether you do anything about it. The mechanical advantage can help you. The disadvantage there is the more times you go round that loop, the larger drum you need on the winch. That's all. It's just longer cable. The important thing is that getting it wrong or not doing it can potentially, literally be life-threatening. So I offer it, guys, as it's your decision. Thank you.